Today we're going to start talking about recursively defined sequences. And a good way to start is to talk about the Fibonacci sequence. The Fibonacci sequence is something you've all probably seen. It's a sequence which starts with the numbers 1 and 1. And then after that, it continues by having each successive number be the sum of the two previous numbers, so that the number after the 1 and the 1 is the sum of 1 plus 1, which is 2. Then you have 1 plus 2, which is 3. Then you have 2 plus 3, which is 5. 3 plus 5 is 8. 5 plus 8 is 13. And it keeps going on and on and on. Here's the way we would write that formally. We let f naught, we're using capital F sub n to denote the nth Fibonacci number. We let f naught be 1, f1 is 1, and then for every n, which is at least 2, f sub n is just the sum of the two previous terms, f sub n minus 1 and f sub n minus 2. We're interested in sequences like this because this sequence itself was first formulated by Fibonacci to answer the rabbit problem, which he posed. The rabbit problem is this. Say rabbits are able to mate at the age of 1 month, and pregnancy takes 1 month. At the end of the second month, a female can produce another pair of rabbits. Assume that rabbits never die and a mating pair always produces one new pair, one male, one female, every month from the second month on. Fibonacci's question was this: if we start with the new pair from birth, how many pairs will there be in 1 year? Well, we start at, say, month 0 with 1 pair. That's what we were given. 1 month later, they haven't had time to give birth because they have to be 1 month old to give birth, so we still have 1 pair. Another month later, we were assuming that they get pregnant, and another month later, we get 1 more pair, so we have a total of 2. 1 month after that, we still have that 1 pair that can give birth, so we have 1 new pair, which gives us a total of 3. But now 1 month later, we have the 2 pairs that we had previously, all of them except the ones that were just born in the last month. So I'll have 2 pairs to add to those 3, which gives us 5. And the pattern continues like that. The next month, we'll have all 3 of the pairs ready to give birth, plus the 5 pairs we had this month, 3 of the pairs from the previous month, so we have a total of 8. And then it keeps going like that. So at the end of 1 year, we have the number f sub 12. And here you see I believe 233 here is what we have at the end of 12 months. Now let me say this problem was posed, and this Fibonacci sequence was first used by Fibonacci, who was actually known as Leonardo of Pisa, and this was a long time ago, sometime around the year 1200, when he wrote his masterwork, which was called Liber Abaci, one of the most important books ever written. At the time, as I said, Fibonacci was not known as Fibonacci. He was just called Leonardo of Pisa. He wrote this book, and the Fibonacci sequence is just one small little kind of side mention in this book. The book contained a lot of great mathematics that he had mostly collected. He didn't produce a lot of original mathematics, though this sequence and the problem are attributed to him. But he introduced the Hindu-Arabic number system to traders and many other people in Europe. He was Italian, of course, from Pisa, though they didn't have something called Italian. There was no United Italy at the time. So he was from Pisa, and he was a trader. So he wrote down these things that he had learned from, and mostly from Arabic traders, and introduced the number system, as well as all the really important basic ways we do math today. Like, how do you add 3-digit numbers? All of us here and all over the world nowadays learn you write them down with our standard numerals, the Arabic numerals. and you add by columns, carrying as appropriate. There was a time back then, in Leonardo's time, when people didn't do that. People didn't have any standard ways of adding or multiplying big numbers. So he introduced this system that became standardized. He did a lot of other mathematics. He introduced more complicated things like how to find square roots, and he talked about some abstract mathematical things like the Chinese remainder theorem, but mostly it was a book that was for use by traders to introduce a uniform system by which they could do the mathematics that they needed to do. And it revolutionized the world. The whole world changed, at least the European world at the time, and this spread in other ways as well. The whole world of European mathematics changed. In fact, it kind of started this world of European mathematics that allowed for all the great discoveries in mathematics over the following centuries. So if you're ever in a class where people study the great books of all time, if they leave out Liber Abaci, which is by Leonardo of Pisa, they've missed one of the really most important books of all time. Let's look at just some other examples of recursively defined sequences. Here's one which looks like a bunch of strange random numbers, but I defined it in the following way. I said here, I'll use the term a sub naught to denote that the first term we have there. I'll say a sub naught is 2, a sub 1 is 1. So let's say I just tell you we start with the 2 and a 1. And then after that, here's the rule that I used. Each time you take 6 times the previous, you take the previous term, which is 1, plus 6 times the term before that, the 1 plus 6 times 2, and you get 13. To get the next term, you take the 13 and add 6 times the 1, you get 19. We'll say that here, a sub n, this is for n greater than or equal to 2, so beginning with a sub 2, which is here. A sub n is just a sub n minus 1 plus 6 times a sub n minus 2. So we can keep going like that. 97 is 19 plus 6 times 13. You can check that that works. 211 is 97 plus 6 times 19, etc. 793 is 211 plus 6 times 97. 2059 is 793 plus 6 times 2011. And you can continue the sequence. What sort of questions might we have about this sequence, and even about the Fibonacci sequence, which we already talked about before? Well, first question that might come to you is there any way to figure out, say, a formula for the individual terms? If I just want to go straight to the 8th term, is there a formula for that? Well, we're going to be talking about that in the some of the next lectures here. But now I just want to introduce this. Other questions that we're going to be talking about is, can we use such sequences in counting problems? And of course, the answer will be yes. That's why we're here. Normally, we're going to have a counting problem, and we'll create a sequence which gives us our answers. And if it happens to be a sequence that has a nice recursive definition of this form, we'll be able to use the techniques that we develop in order to find formulas for the answers. Here's another simple example that we're going to look at later. We're going to start with a0 equals 0 and a1 equals 1. And then the rule will always be to take 3 times the previous term. So this is for n greater than or equal to 2. A sub n is 3 times the previous term, a n minus 1, plus 2 times the term before that, a sub n minus 2. So 7. I'm sorry, not plus. It's going to be minus. That's where it's going to be fun. So let me say that again here. We start with the 0 and 1. The 3 here is 3 times 1 minus 2 times 0. The 7 is 3 times 3 minus 2 times 1. The 15, you take 3 times 7 minus 2 times 3. And we keep going like that. 31 is 3 times the 15 minus 2 times the 7. And we keep going and going. You might recognize this sequence as well. I won't give it away right now, but we'll solve for it later. But these are numbers that should follow a familiar pattern. what do you see about this sequence here, and the previous one, the Fibonacci sequence? The first thing I'll just throw out for you is that they seem to grow very rapidly, kind of like a geometric sequence where each one is some multiple of the previous one. Of course, there's no one particular number where each term is that particular number times the previous one. You'll see that the ratios of the individual terms differ, but are kind of similar. Especially for this last one, you notice each term is just about, in fact, just over 2 times the previous term. Here, each term looks like it's growing by some reasonable multiple times the previous term, but it's a little harder to see exactly what that might be. And the same is true for the Fibonacci sequence.